Start another one? Huh?
Sure. Look at
I can show you.
I think most people has already gone
Yeah, it's the regular same thing.
Come on. Yeah, come in way.
Oh,
yeah, it's coming as a way. Please sit down. Hello, chair.
Thank you.
I got you.
Sit down.
Okay.
Thanks for coming, everyone. My name's Jeremy. To my left, I have Abhinav, Kwai, Dustin, Winter, and Ryan over there on the end. The video you just saw is one of the projects we're working on here at the ADAC lab of NC State. It's called Intelligent Space, or iSpace for short. And this presentation is going to be discussing iSpace. Dustin's going to give you a little bit of background on iSpace and what it's all about.
So some of the motivation for a project like this is mainly just collision avoidance. I'm sure everyone knows of someone that's fallen asleep at the wheel while driving or has been in a general car accident, and something that we'd like to do is completely eradicate that. And a way to do that would be if every vehicle on the road knew where every other vehicle was and vice versa. You could keep those vehicles apart with some main controller that would keep them from colliding. And another reason is you'd be able to just get in your car in the morning and say, I'd like to go down to Wilmington or the beach, and fall asleep and let your vehicle take you there without ever having to do anything, and you wouldn't have to worry. You'd be able to travel at much higher speeds, and you'd be able to be much closer to other vehicles because computers can react and behave so much faster than humans can.
All right, thanks for that, Dustin. Now let's talk about how our iSpace works here at the ADAC lab. So we have this trackable region which you see on the ground in front of you, and there's several robotic cars which are traversing this track. Their current position and orientation is picked up via a sensor system. The cameras of that sensor system are actually mounted on the ceiling. That sensor system picks up those tracking coordinates and sends them to a controller, which figures out where is my robot located now, where does it need to go, and communicates that data between each robot so that that robot can get to its end destination. So you may be wondering at this point, How do I decide what the end destination of each robot is going to be? We have a graphical user interface where that data can be inserted. So let's talk a little bit about how the sensor system works. The sensor system we use is called OptiTrack, so I'm going to tell you a little bit about that. So if you direct your attention to the robotic car in front of me, which has the plastic balls mounted on it, these plastic balls are called markers. We combine those markers into different geometric shapes, and those become what was known as a trackable object. The cameras mounted on the ceiling pick up those trackable objects and send the images to image processing software called tracking tools. That tracking tool software has the capability to discern the trackable objects from the surrounding environment, and because of that, it can figure out what is the position and orientation of each robot. That data is then sent to our controller, which figures out where is the robot located now, where is it trying to go, and how do I get from location A to location B. So now Quad's going to tell you a little bit about how the camera system works.
Hi. So if you look up, there's 6 of these red cameras on the ceiling, and each of them are infrared cameras, and they emit infrared light, which are reflected by those round spheres, the markers over there, and picked up again by the sensors in the middle. So a little tidbit about the cameras. They're the same cameras that they use for shooting movies like Avatar, where you put balls on people's faces and also on their joints so that you can get their facial expressions as well as map their athletic movement. So instead of mapping things like that, we're mapping the location of robots. And how it works is if you have 3 cameras looking at a particular marker at the same time, then it is able to triangulate its position in 3D space, kind of like how GPS works. So by doing that, we're able to get its position and orientation in 3D space in real time. So I'm going to give it to Winta, who will talk about how the robots actually work.
Thanks, Quan. And actually, the parts we're using to build this robot are all from the LEGO milestones. As we can see, we have 2 motors to control the left wheel and the right wheel, and we have 3 light sensors to detect the black tape in this track. We also have another motor to control the ultrasonic sensors, which is used to detect the other robots on this track. So for the language, we are using the Java programming language to implement all the control algorithms in these NXT bricks. So with all this software and hardware, we can implement the robots to track the black tapes in this track. So now we will show you a very short demo to show how this system works. Thanks.
So if you guys direct your attention to the computer screen over here, we're able to, the thing labeled Trackable 1 is actually that robot over there with the markers, and we're actually able to pinpoint its position and orientation. Sometimes we lose tracking, but it could be because of the ambient light that we have in here. And also it's been running for a while now, so the computers are a little bit tired. So over here we have the position and orientation in 3D space, and that's that robot right over there.
And you guys may notice the red and green lines along the track. These are used to help us implement traffic logic. Basically, when a car approaches a green line, if it's going straight, it'll remain going straight and it won't slow down. However, if it's wants to make a turn like this car does over here, it'll stop and check for any incoming traffic. And once it sees no traffic is in the vicinity, it'll turn. And at the red line, that's basically a stop sign. So whenever a car approaches that line, it automatically stops and checks for any traffic.